Hello everyone, warm welcome to ICNTE 2021. Today I will present my research entitled Multi-Parameter Optimization of a Hemispheric Angle Diversity Receiver to Reduce SINR Fluctuation for an Indoor MIMO-VLC System. So these are the outline of my work. Straightforward, I will move to the introduction of my work. Future wireless network have to deal with a high degree of heterogeneity in terms of defined classes. Mobility levels coexisting wireless technology is an encouraging approach to revolve the future network. The radio frequency based Wi-Fi access points have already been discussed or considered to enable indoor traffic loading from LTE cells. In addition to RF, VLC and its network counterpart Li-Fi open up a completely new paradigm, new opportunity. VLC is an encouraging and emerging technology that uses existing lighting infra to offer high data transmission combined with the excellent quality of illumination. Moreover, it's a green technology, completely unregulated and license free, that can operate in between 400 nanometer to 800 nanometer. So, what is the state of the art research in last few years? Motivation behind this work. First of all, improved data rate. MIMO techniques are well established and widely implemented in RF system as they offer high data rates by increasing the spectral efficiency. Unfortunately, off-the-shelf LEDs provide very limited bandwidth of 20 to 40 MHz for VLC. Consequently, these incoherent light sources restrict the available bandwidth of the practical OW system. So, in last few years, ongoing research activities intend to increase the capability of the OWC system through multiple input, multiple output communication technology, where a number of light sources act as a transmitter and number of photodiodes acts as a receiver, but provided MIMO channel matrices has to be highly uncorrelated, especially in case of multi-cell indoor VLC system. But in reality, in the indoor VLC system, these channel matrices are highly correlated. As a result, it creates interferences as shown in the figure. Surrounding LED actually create interference when a signal is received from a certain LED. As a result, SINR get reduced and bit error rate increases. So to get rid of this stagnant situation, some amicable solutions are proposed in last few years, that is angle diversity receiver. Two types of angle diversity receiver has been proposed. One is pyramidal and another is hemispheric. In this work, strictly we will discuss about this hemispheric receiver. So what is the objective? Objective is twofold. Number one, we want to improve the average SINR using a hemispheric angle diversity receiver by adopting optimal field of view of the photodiode. And number two, reduce the SINR fluctuation causing due to the random rotation angle of hemispheric ADR. So you have to understand what is random rotation angle. So look at the HADS structure. Here we can see 5 photodiodes are used, one at the top and 4 at the side. In a nutshell, we can consider some points on the surface of a hemisphere to determine the normal vectors of the PDs. We firstly evenly distributed these points. Here 4 side photodiodes are used. So 4 side points on the surface of a hemisphere are 90-degree apart as shown in this figure. Now the coordinate of each side photo detector is represented with this equation, where azimuth angle of the jth side detector is represented using this equation. Here we can see a term theta RRA, that is random rotation angle. What is random rotation angle? Suppose an user place this particular angle diversity receiver, and due to the placement, the photodiode may be shifted by a random angle. So this angle is random rotation angle. It may be 0 degree, starting from 0 degree to 90 degree. Anything can happen when it is placed over the communication floor. So this angle represent the random rotation angle, and this is a completely probabilistic event. We cannot measure exactly what is the random rotation angle, but due to the different random rotation angle, it has been observed the SINR fluctuation is different. So we want to design a certain hemispheric angular diversity receiver, so that irrespective of the random rotation angle, SINR fluctuation is limited within a certain threshold, and as well as we can get the average SINR at a very high level. So these are the system model. Here you can see the channel gain is dependent on the two parameter. One is the angle of irradiance and number two is the angle of incidence, and this d omega is the solid angle. This is commonly known to Li-Fi researcher, and here AR is the active area of the PD, and the electrical signal obtained at the jth receiving element is represented by this equation, where this HLOS IJ is the channel gain, PTI is the transmitted power from each light source, mu is the modulation index, and gamma is the optical to electrical conversion efficiency. Now we have used select based combining scheme to receive the actual signal. So that means we will receive the signal from a LED, from where we will get the maximum signal to interference plus noise ratio. So always at each position over the communication floor, we want to adopt this SBC scheme, so that the SINR level is high. So the signal to interference noise ratio over the communication floor is represented by this equation. Here the numerator is the signal strength and the denominator is the noise strength. Here N total is the total noise occurs due to the short noise and the thermal noise of the photodiodes. Now the spatial SINR fluctuation over the communication floor, again it is the maximum SINR it may obtain at any point, and the difference the minimum SINR, and the spatial average SINR is the sum of the SINR at all points divided by the 400, because we have taken 400 grid points over the communication floor. The average SINR deviation due to the variation of the random rotation angle is described with this equation, and we have taken 1 degree interval for the calculation. Now proposed optimal field of view of the HADR. So why optimal field of view is used? So reduced field of view angle always eliminate co-channel interference. As a result, signal to interference noise ratio always improves. However, if we continuously reduce the field of view in an uncontrolled fashion, it leads to blindness of the received signal. So what is the solution? We have to select a particular optimal field of view, so that we can get the signal, and as well as we can restrict somehow the co-channel interference. So this optimal field of view is determined with this objective function. In previous work, this beta has not been considered. So in this objective function we have included the beta, that is the inclination angle. Irrespective of the inclination angle, we have defined the optimal field of view so that the receiver can receive the signal at any position, that means at any xh, yh, zh position over the communication floor, and as well as the any beta. Now what is my motto to include this parameter beta? Because we want to see how the spatial SINR deviation or average SINR deviation depends on the beta. It can be described by this figure. In this figure we can see the average SINR deviation is lower at beta equal to 10 degree, and we have included, or we have defined a term, that is spatial SINR consistency factor. It is maximum at 10 degree. So spatial SINR consistency factor is a probabilistic parameter. It is defined as the probability of getting SINR deviation below a certain threshold limit when RRA is varied from 0 degree to 90 degree. So this is the results. The obtained optimal field of view is 32.93 degree. Now Here we can see this is the formula to determine the SINR consistency factor. So from this figure it can be explained very clearly. So these two are the non-optimized case. Here you can see at beta equal to 30 degree, the impact of RRA, that means random rotation angle, over the spatial SINR deviation. We can see when the random rotation angle in between 0 to 10 degree, the spatial SINR deviation is very high, as well as when it is 30 to 60 degree, again it is high. But so that means it is all time changing depending upon the random rotation angle. So this is not a optimal solution. Here the consistency factor is defined as the sum of the lower portion, that is below the threshold, that means B1 plus B2, divided by all the portion, that means A1 plus B1 plus A2 plus B2 plus A3. Here we can see. So, and the threshold we have taken 10 dB. So we have considered if the SINR deviation is below the 10 dB, it is good. So that means maximum SINR consistency factor is 0.978 is obtained at 10 degree inclination angle. It is shown in this figure. In this figure it has been shown. Here you can see for 10 degree inclination angle we are getting a constant SINR deviation, and that is also below 10 degree, very minimum. So this can be considered as an optimal solution of a HADR, proposed HADR, that is psi c of, that means the field of view is 32.93 degree and beta is 10 degree, inclination angle 10 degree. We can see at unoptimized condition SINR may fluctuate. Here we can see the SINR is fluctuated over the different grid points. But in case of the optimal solution, we are getting a steady SINR in between 45 and to 53 degree. Finally, the conclusion, we have investigated the technique to combat the spatial SINR fluctuation of a multi-cell MIMO-VLC system. In comparison with the earlier work, where 15.7 dB SINR deviation has been proposed, we offer 5.17% reduction in average SINR, simultaneously 48.81 dB average SINR is obtained. So we can say our proposed design, we 10 degree inclination angle and 32.93 degree optimal field of view can provide excellent communication performance by negating the random error contributed by the random rotation angle. Thank you everyone.